talked about how we could build up the capacitance from geometrical arguments and understanding the relationship between the electric field and the electric potential. And that same equation, the V is going to be equal to the negative integral from r vector 1 to r vector 2, if this is some change in electric potential, of E vector dot dl, is also the way that we're going to talk about resistance. And so we need to lay out a couple of equations first. The first one is what's called the microscopic form of Ohm's law. So this is going to be E is equal to rho J. So this is the microscopic Ohm's law. Okay, where J is the current density vector. And rho is the resistivity. So you have to be careful here because the resistivity can look a lot like the volume charge density, both in the fact that they're the same letter, and because geometrically a lot of these problems look very similar to Gauss's law problems. So you want to be very careful when you're reading the problem statements on the exam to make sure that you're doing resistance calculations for when you have a resistivity, and you're doing Gauss's law calculations for when you have a charge density. Okay, well, let's look a little bit more at the current density vector and think about what this actually means. So imagine we have some grouping of charge like this, and it's moving. So part of the notion of the current density is how tightly packed the charge is together, and the other is what direction is it moving. So you could say that this would have some current density if these were like positive charges. Imagine these are all positive charges that are moving down, and this would have a different current density if these were positive charges moving to the right. So these ones are less tightly packed than this one, so the value of the current density is smaller, and then the direction of the current density is different. Okay, so that's the microscopic form of Ohm's law, and what we're ultimately going to connect this to is the microscopic form of Ohm's law, which is an equation you might have seen before. So in order to do that, we're going to lay out a procedure the same way that we did in the capacitance section. So the first thing that we want, so this is how to calculate resistance. Okay, so the first thing that we want to do is write down the microscopic form of Ohm's law. So E is going to be equal to rho J. 2. We want to think about the relationship between the current and the current density vector. And so that says that I is going to be equal to the flux of the current density vector. So that's the relationship between J and I. And this kind of makes sense on an intuitive level because the flux we saw when we were talking about electric field, it's like a count. You're counting electric field lines. Here, I'm counting the charge per second per area, and that gives me the charge per second. All right. So the next thing that we can do is we can combine these two. So we combine 1 and 2. And then from that, we'll have some expression for the electric field in terms of the current. And we can say that the difference in electric potential, delta V, is going to be equal to the negative integral of E dot dl from r vector 1 to r vector 2. And the last thing that we can do is we can say that the we have the macroscopic form of Ohm's law. So V is equal to IR, or R is going to be the ratio of I to delta V, the magnitude of delta V. So let's see how this works in practice. So imagine we have some resistor like this that has some resistivity of rho, some cross-sectional area of A, and some length of, let's call this an L. Okay, so we have this physical resistor. We want to calculate what its resistance is. So what we can do, write down first, microscopic form of Ohm's law, E is equal to rho J. Second, we write down the relationship between the current and the current density vector. And what we want to do here is we want to consider, well, if we're making charge flow here from the left side to the right side. So imagine we're making charge flow from left to right. Then here's a bunch of charges that are moving to the right, and they're going to pass through some surface like this, where this is going to be our dA vector pointing to the right. And this current density we have is constant over the entire cross-sectional area. And it's also in the same direction. So what that says is that I is going to be equal to J times A. And so then we can say that J is equal to I divided by A. And so combining these together, we can say that E vector is going to be equal to rho I divided by A times X hat, if this is going to point to the positive X direction like that. So now what we want to do is we want to find what the difference in electric potential is between these two ends. And so we say that delta V is going to be equal to the negative integral from R vector 1 to R vector 2 of E dot dl. And so in this case, this is going to be equal to rho I divided by A times L. Okay. So that is going to be V. And so we also know that this is going to be equal to I times R. So I'm kind of combining step 4 and 5 here. But step 5, we're going to get this right here. And what we could do is we could cancel out our I here. And so that what this says is that the resistance here is going to be rho L divided by A. Okay. So that is the process that you go through in order to calculate resistance. And you might have seen this equation before here. So you do want to be careful. You never want to use this equation, right? This is only true for this resistor. So if I did something spherical, or if I made this resistivity vary over the length, or did something slightly different, then this equation doesn't hold. The process always holds, but this equation does not always hold. All right, so that's it for this video. Take it easy.